Good morning, everybody. I'm trying not to take up class time with logistics, with announcements and that kind of stuff. As you all noticed, I send announcements through Blackboard. So when I do send them, please try to make sure that you receive them, whatever setting you need to do in Blackboard. I sent one out last night, making sure that you guys were aware that there was a pre-class quiz for today. I saw about half the class hadn't done it when I sent that out. Most people had done it by the end of the evening, so that's great. I'd like to keep consistency, but more importantly, I like to make sure that we're progressing through the semester, so I'm trying to balance those two. So I apologize for things not always being the same order every week. I'll do one or two logistic things in a minute here, but we'll try to get you guys prepared for our first test, which is next Monday, which does include some quantum, so we'll kind of get rolling towards that. Okay, this is the second to last question that was on your worksheet from last class, but I also put it on the top of this new worksheet from today. So chat with your neighbor, see if you have come to the same conclusion. I'm going to see if I can pull it up on my phone. Alright, you guys are not in agreement at all. No. Come on, convince your neighbor that your answer is the right one. Can I hear from someone who might have changed their answer because they were convinced so by someone sitting next to them? Some of you might have missed in the wording of the problem or with the answers here. Yeah, Aaron?
I wasn't in the group with them, but I remember what they were talking about. So originally I had my answer be based on the Bohr model of the atoms, where it looks like every single step releases the same amount of energy. But then I heard what they were saying, and I looked up at the thing, and I saw that what you're looking for is the least amount of energy released. So B would be incorrect because it releases a energy.
Okay, great. So there's two components of that I want to tease apart. One is the relationship between wavelength and energy. What's the equation that relates those two to each other? Can I have a hand-raised volunteer for that equation? Matthew?
Energy equals the speed of light divided by wavelength times the height.
Times Planck's constant. Okay, so Planck's constant is a value that relates energy to frequency or energy to the wavelength. So if we're talking about the longest wavelength, that means the biggest number here. What does that mean it's going to be the energy? Is it going to be the largest transition of energy or the smallest? Smallest energy, because it's an inverse relationship between these two. The larger the denominator gets, the smaller the overall number gets, and we're talking about, on this axis, we have energy, and here we're talking about wavelength. So this question is really asking, which is the smallest change in energy? But there's a second component to it that makes it a little bit more tricky than that. What's the second piece of the wording of this question that actually rules out half of these? Amber?
You're looking for which ones emit light, which are usually the ones that give out energy, so you go from higher levels to the lower levels.
Fantastic. So the emission of light only happens when an electron starts at a higher energy level, relaxes down to a lower energy level, and in the process emits light. It has an emission. So if you're going from 1 to 2, this couldn't be an answer anyway because it's absorbing energy. It goes from 1 to 2, which means we need to absorb light, not emit light. So right off the bat, we can say not at all. Are there any others we can cross off? So then the question is 4 to 3 or 3 to 2 a smaller change in energy? Based on the diagram that we have here. 4 to 3 looks like a lot smaller, which is this infrared. I know that's not going to show up. The infrared versus 3 to 2, it's red light. Eric?
When we do that equation, is wavelength in nanometers or meters?
Can be in anything you want. So when we actually do the calculations, we want to make sure if I was to ask you the specific value of that, we would need to use the wavelength in meters. But we can talk about bigger or smaller relative for any unit as long as we know what the prefix means. So this constant is how we relate the two. So we could do the calculations if we want. This question was not about the calculations. I haven't had you guys do problems on the calculation of what the energy change is. It's called the Rydberg series. It's not as important as conceptually thinking about the relationship between the wavelength of light and energy and how those are inversely related.
So that equation right there, the E, how does that relate with the change? What would you be using with that equation to solve? Is that change in energy?
Yeah,
Or
so
is that
these,
like as
well, so there's two ways to look at it. It's either the change in energy between the two energy levels, or it's the energy of the photon that comes from that change.
Okay.
Either way you can look at it, it's the same outcome. And so here we're talking about if you start here, and come back to from 2 to 1, then this is the amount of energy, the change in energy released, which is the energy of the photon that's sent out. And if you notice, there's actually a 0 for energy up here. Anyone notice that? And then the numbers all become negative. Does anyone know why that is? Because what?
All the arrows are going down, they're losing it.
Well, so this particular image, they're all showing the electron going from a higher energy level to a lower energy level. Yes? Trey?
It's negatively charged.
It's a good idea. And so I think it kind of relates to what Joey was getting at.
You're starting on the right side of the spectrum, but you're going to the left, so you're losing.
So, yeah, and if we think about, this is talking about the attraction of an electron and a proton, or the nucleus, whatever the nucleus is. So if we have the electron way out here, we say that there's, this is our 0 point in energy. If we release that electron and allow it to come closer to the nucleus, the closer it comes, the lower energy shell it goes into, the more energy it releases. And so this is how much energy is released, and this is per atom. It seems like a big number per atom. I want to say it might be per mole of atoms. But conceptually, I want us thinking about the more stable something becomes, the energy to get there means it's being released. And so we're going to have a decrease in energy of that system because the energy goes somewhere else. It's sending the energy out because it's becoming more stable. So this is the kind of question that I would expect you to be able to answer next Monday, as well as something a little more complicated, like the second one. I'm going to give you 1 minute and 30 seconds on that clock to answer this question. Talk to your neighbor if you'd like. I would advise thinking about it conceptually before trying to crunch a whole bunch of numbers. we have 30 seconds left. Make sure I think conceptually on this question.
Some math. You're saying it's not equal going up as it is going down.
Need another 20 or 30 seconds? Yeah. Okay. We'll go to 2 minutes and then we'll shut it down. So you know the 2 photons that came in. The question is, what is the photon going out? Sorry. All right, we're at 2 minutes. Go ahead and close this one out so we can start talking through it. Jason, there should be some extra worksheets back there. If not, they're up here. All right, so this does not look like consensus. This looks like a whole bunch of answers all over the place. So how do we go about this? Can I hear someone's approach they use to try to figure out how we'd approach a problem like this? Josh?
I went really basic. It said it accepted 2 photons, it told you how much they accepted, and then it relaxed. So it's going to always go back to the inner shell. So it released 2400.
I love 90% of what you're saying. Okay? And this goes back to what, I think, was it Eric's I saw? That was this equation. This is kind of what you're getting at? That the amount of energy that goes in is equal to the energy that comes out. Conservation of energy is something we're going to be really focusing on this entire semester. Conservation of mass is another. So the amount of energy that gets put into the system has to equal the amount of energy that comes out of the system. So if we put in 2 photons worth of energy, that means that those 2 photons, the total energy of those, has to be equal to the energy of this photon that comes out of the system. So where is the little 10% tweak that we missed in that description? Can I just add together 800 plus 2400? What is 800 and 2400? What are those measuring? Wavelength. How does wavelength relate to energy?
It's inverse.
Okay. So now, without doing any calculations, I want you to think about the relative energy of all of these options. There's only one possible answer it could be out of those options, based on the relative value of energy versus wavelength. That inverse relationship. So I've reopened the poll, talk to your neighbor, try to figure out why only one of these answers can be correct, and it is not 3,200 nanometers. I think you're on the right track. I just wanted you to be careful with addition and using wavelength. So you might have. All right. Can I hear from someone who thinks they might have figured it out by kind of working through that? Kevin?
I have no idea how I got the number itself, but visually looking at the length of the wavelength from the crest of one wavelength to another, I could see that how long 2400 was from each crest, and then how long 800 was from each crest, and seeing the distance on the third wavelength is even shorter than 800. Process of elimination, it would be 600.
Okay. Legit. You use the visual cues you have. Okay, so which answer did you choose? You chose D, 600 nanometers. Correct. Okay. Totally legit. What about conceptually talking about wavelength, that kind of stuff? Tripti?
Can you explain again how we got 600?
So all that Kevin was saying is that this one has a very long wavelength, this one has a shorter wavelength, and this one has an even shorter wavelength. So visually, done. Trey?
It would have to just release a greater amount of energy than the summation of those two.
Oh, did everyone hear that? Say it one more time.
It would have to release a greater amount of energy than the summation of those two that it absorbed.
Careful, I'd say not greater than the sum. It has to equal the sum. So the energy that goes in, right, we put in this amount of energy and then a little bit less energy. So then the energy released has to be equal to that. So how does the energy of this photon compare to these two? Is it bigger, smaller, in the middle, the same as one of the two? The amount of energy released by this one,
The energy is greater.
it's greater because it's the sum of these two. So if the sum of these two is bigger than either one of them, that means the wavelength has to be greater or smaller than either one of them. Smaller because it's inverse. So the only wavelength out of all of your options was the one that is a smaller wavelength than the two that went in. Joey?
Can you show me how to do the math? Because I really don't trust the pictures normally in books because I'm wrong. Honestly, I don't. I mean, it makes sense, but it doesn't make sense to me.
Okay. So the take home for the math, and we're going conceptual here. You could also, could you calculate this? You could actually calculate what is the energy of this photon. So you would do energy of photon 1 is hc over 800 nanometers. Okay. We have speed of light is c, Planck's constant is h, 10 to the negative 9th meters because it's nanometers. We could calculate that. We could also calculate energy of photon 2. hc over 2400 times 10 to the negative 9th meters because nano is negative 9th. And then we could add together E1 plus E2 equals that third energy of the third photon. But that energy of the third photon, that isn't even our answer, right? How do we have to find our answer from that? We'd have to go back and then say energy 3 equals hc over lambda. We don't know this lambda, right? That's this question mark. And so if I ever ask you this question on a test, which I've been known to do, every test I've ever given on quantum, you're not going to have time to do all these calculations. That's my point. I want you to think about the inverse relationship between wavelength and energy and use that to decide what is the only possible answer. There will only be one that is possible, the way that I give it to you. And so you have to understand that inverse relationship, that wavelengths are not additive. The energy is additive, and so we have to think about what's the relative energy of each photon. Smallest energy is the second one. This is the second smallest, is the first photon. And that third photon is the largest energy out of all of those, so that means it will have the smallest wavelength. Questions? All right.
I'm still not.
Okay, so if you are still having a hard time with this problem, I've only been seeing like one person at office hours every time I have it, so I would love to have 10 people in there discussing these things. So I have office hours Monday, Tuesday, and Friday. I have additional availability upon request. There are people upstairs to help you in the tutoring center. There are study groups, so there's a lot of things. So next week, Monday, you need to be comfortable with this. You don't have to be comfortable with it right now. All right. So this was one of our learning objectives for today. Distinguish the relative relationship. It's the relative relationship that I'm most interested in between energy, frequency, and wavelength. And determine if I had asked about, if I'd shown you frequencies in that last slide instead of wavelength, think about how that would be different. So maybe take a note, go work on that afterwards with your friends. So if we had been given frequencies, would it be the biggest or the smallest frequency if they are all relative like that? So we're going to spend some time now contrasting Bohr's model with quantum. It means we're going to spend some time with quantum, which we haven't done too much of yet. That means you're going to be able to describe the 3D probability distribution, or the wave function for electrons, which contrasts Bohr's model. And then we're going to start filling atomic orbital diagrams, which are on the back of your worksheet. Today is exactly 1 week from our first exam, so that means we have 3 classes this week, and then we have our exam 1. All the exams are equally weighted. What I should probably do is in the next couple days complete the draft of our exam and then post maybe some previous exams that I've had for my classes so you can get a feeling for what our exams are going to look like. Because I'll be posting previous exams, it means that the content might not exactly match. It's not going to be a practice test. It's going to be old tests because I'm not going to make 3 tests to give 1 test. The homework should guide you pretty well in practicing the skills. There is a homework that is due Wednesday. So we got a lot of stuff kind of coming together on Wednesday. We're still moving forward with new materials. That means we have a pre-class quiz Wednesday, Friday. We have our homework 3 that I pushed back because we've been taking some time getting into quantum. So homework 3 is due Wednesday and our post-quiz is due Wednesday. So all that you can work on ahead of time. Homework 4 is due on Sunday night the night before the test. And then we don't have a post-quiz this week because we have a post-test, if you wanted to say it that way. So Monday's a test, so there's no post-quiz for homework 4. Eric?
You're going to have the rules for electron configurations in...
We're going to be working through those. I do not give you rules. I do not give you equations. On my test, I haven't got any pushback from this yet, so we will be having a note card. And so you can bring a note card, handwritten, your own note card. I collect them at the end of the test, so you cannot use them again. It's the process that I encourage you to use, studying, looking at what was important in previous classes, making sure that you focus on what is the most important thing. You can write that down. And honestly, during the test, most people don't even use them. Most people use it as a study tool that kind of helps them focus and prioritize. And then when you take the tests, it's there in case you need it, but most people don't need it. And I want to show you one thing in OWL. I'm not sure if everyone's been using this so far, but if you're in the homework, there's the review topic at the very top of the screen. If you click on that, there's some really, really, really good resources. And specifically the Sims.
Is this in the practice only?
No, this is in the homeworks specifically. So the homeworks have these. I don't know if the pre-class activities have them. But what it does is it basically walks you through a series of questions that helps you figure out what that concept is talking about. There's also links to the book from there. There's a whole bunch of other things as well. But you can kind of walk through some of the concepts if you're not comfortable with it. And you can fill in atomic orbital diagrams. It has a whole bunch of things that you can do. So I highly recommend checking those out. Angel?
I finished the homework already, but if I want to go back and do some more of those problems,
Yeah.
I didn't feel totally confident.
Homework 3 or 4? Probably 3, the ones due on Wednesday.
Yeah.
So as soon as the homework closes, I believe it is open for practice. And so you can go back and redo practice as much as you want.
Change my score.
No, it's practice. It literally says like click on this to practice.
Okay.
I was gonna say something about that too. One thing I realized is like, once you take a test and it's submitted, I can't see the thing again. Like it just completely disappears and moves on to the next week. If I wanted to go back and look at those weeks that we've done before the test, could you like, is there a way you can open
So I think what you're talking about is that the standard view for assignments only shows what's due. You have to go up to the top and click view all assignments, and then it gives you a list of everything, not just what's due. I think it distills down the homepage so it's simplified for you. That's a good point. So make sure you go back and look at your old assignments and you can practice this. There are also all of the end of chapter questions that are literally dumped into bins. So you can go look at all of the chapter 2 end of chapter assignments. Basically like looking at the end of your textbook, the end of the chapter, and you have all those questions. It means you need to decide which ones are relevant. I haven't gone through and selected out the specific questions to do practice on, but you can go through those and skip questions that you don't think are valuable. So those are, you won't see those unless you go to the view all assignments as well. And they're called like chapter 2 end of practice or whatever they're called, end of chapter questions. For those of you who are interested in quantum and want your mind blown, I'm going to post the slides after class. Seriously, check out this video. I wish we had time in class to go through this, but we don't. It talks about some experiments they've done and how bizarre quantum is on an everyday kind of scale. So let's start with a clicker question here. What do you think about this statement? Electrons have mass and are particles. Hence, electrons do not act as waves. Couple more seconds. True or false? Click in your response. Closing out. Okay, so we're split 2-1. Let's watch a little video to help us out with this. And hopefully we can get audio. Let's see if we can do this.
You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit.
The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller.
You can picture them like this. Let's see what happens if I throw a bunch of these balls.
What do you guys expect?
I already know the answer to this.
Yeah.
You expect 2 lines? Remember what happened when we shone it through? The 2 slits?
Electrons are hurled at the 2 slits. Something very different happens on the other side. Instead of hitting just 2 areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the 2 slits, the very place you'd think would be blocked.
Does that mess with your head a little bit?
No.
So, what does this mean? Talk to your neighbor for a second. What does this mean, the fact that we take particles that have mass and we end up with that pattern? Anyone want to share their thoughts? What's going on? Go ahead, Jackson.
Every single particle, massless or otherwise, okay,
in quantum mechanics has something called the de Broglie wavelength.
So,
I don't know if that's how you pronounce that, but
and if we summarize how that influences the
but it
result we
basically
saw
means
here.
that every single particle, including electrons, has a wavelength and therefore can act like a wave.
Perfect. Does that mess with your head?
Yeah.
Physical particles act as waves. The smaller they are, the bigger the wavelength is. And the more they act like a wave, and the more we would see an interference pattern. Try to wrap your head around that. And basically what he's describing here, that video I just talked about on the last slide, that goes through a whole bunch of different variations they did of that experiment by trying to like put a detector on one of the slits, by looking at turning the detector off but still having a whole bunch of stuff that's super cool, and the results are just mind-boggling.
Are these, I guess, transferring electrons, or are these the ones that are actually orbiting elements?
So these are electrons that are being transferred. They're being...
That's what acts like waves. It's the ones that, from what I was taught, the ones that are orbiting, they are attached in some manner, and they...
So we'll get into how that then relates. Good transition. I appreciate it. So let's watch the end of this video.
Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described.
Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave.
That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron, I can never predict where it will land. But if I use Schrödinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on. These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise, so long as you can accept that it's all about probability.
You guys' heads hurt yet? So if we go back to the quotes I had from Richard Feynman the other day, this is kind of where I was getting at, that we observe some incredibly bizarre things that happen with matter and with light, and a lot of similarities between those. And what I want you to be able to do is to be able to utilize the trends that we've seen in the past in order to describe physical characteristics of things as we go forward. So thinking about Schrödinger's equation, and if you guys are curious about this equation, you can just take some physical chemistry classes and you'll spend days and days and days of time trying to manipulate this equation. It's exciting. It took a semester of nothing but physical chemistry. And it was very interesting, but I wanted to kind of gouge my eyes out towards the end of it. But what he found, what basically the group of physicists found and chemists, is that we can describe the probability. Where is the most likely place, or how probable are we to find an electron if we look in different areas? And out of that came a set of descriptions of wave functions. And so the wave functions have multiple different shapes, and this is kind of a heat map of the probability of where we find them. So this is, what do we call s orbitals, these are p orbitals, these are d orbitals, and these are f orbitals. And we gave them different names based on some of the shapes. But we'll kind of talk through them one at a time. These shapes that we're talking about are not just balloon-looking things like you see in your textbook. I wanted to show this image because it really looks like it talks about a heat map. Where is the highest probability and the lowest probability of where we're going to find an electron around a nucleus? And so we'll be talking first about s orbitals, but I hope you can see here that it's not a spherical shell of where the electron is. There's a density probability of where we're likely to find that electron. So s orbitals are some of the first ones that we'll find. S orbitals are spherical in shape. As we go up from 1s to 2s to 3s, hopefully you guys will notice the size gets bigger. That just means that the probability that we'll find an electron further from the nucleus increases. I want you to use that term probability whenever we're describing any of these different orbitals. Quick comment?
Yes. So if I get this right, okay, so if you have a 2s orbital electron, then would it be more or less probable that it could end up, that it could also end up in the middle of the 1s shell?
So
will it be more or less probable? Like, is it a ring, or is the probability?
So we can discuss this a bit more in office hours, but there is a node where there is zero probability between the 1s and 2s, but there is some probability in the center of the orbital as well.
Okay, that's the answer.
So this is kind of a dot matrix version of that heat map we saw on the last screen, x, y, and z axes. The blue dots represent where, if we're going to do look for an electron 1,000 different times, each dot represents where we might find that. So then why do we represent it like a candy shell instead of like this on the left here? Any ideas? Why do we show it in these spherical forms? Savannah?
Is it because it gives it more of like a definite boundary?
Right, and it doesn't have one, so why do we give it a definite boundary, I guess is my question.
To see the increase better?
Great, so it helps us kind of visualize, well, where is the volume in which we're likely to find these electrons? And honestly, the candy shells typically represent where we're likely to find the electron 90% of the time. And then they just kind of put a candy shell around that to help us visualize that space, the area in the volume in which that probability exists. When we go from 1s to 2s to 3s, that volume expands. Okay? So these candy shells are not, the electron is not that shell. I want to make sure that we're not mixing that up. If we look at the distance from the nucleus and how probable we are to find an electron as we go further and further out, at the nucleus itself, we actually don't have electrons because they're not up against the nucleus. There's a little bit of space. As we go further away, this is a distance in picometers, 10 to the negative 12th meters. There's a certain maximum probability of finding the electron, and then as we go further out, that decreases. So if you notice here, that candy shell model kind of just cuts it off at a certain point and says, okay, this is where we're going to draw the shell. But there still exists a probability of finding that electron outside of that shell. If we look at 1s versus 2s versus 3s, here's 1s probability, 2s, and 3s. What are two things you notice about the difference between those graphs? Talk to your neighbor for a second. What are two differences you notice between the 1s, 2s, and 3s orbitals and their probability distributions? Can I hear from Marquis? What did your group discuss?
Well, at least to say that each graph, the further away you get, the more, I want to say, differences in the orbital. I don't remember how she put that. I'm not even,
So you're trying to get at that as you get further away from the nucleus, you find higher probability in the larger orbitals. Is that an okay way to say?
Yeah.
So if we have n equals 1, we have a very low probability of finding the electron past a certain point, which is the point, I'm going to do the same point in all three of them here. Okay? So we're more likely to find the electron further from the nucleus, the higher number we are in. We're going to call them shells, n equals 1, n equals 2, n equals 3. Okay? Eric, what else?
The outer shells seem to be more diffuse.
Great. So if you look at the probability, it's much lower probability at any particular point, which means that electron is found in a probable to be found in a much larger volume. More diffuse is another way of looking at that. Savannah?
So the orbital is where the electron can be found?
It is where we are most likely to find the electron, or the probability of finding the electron at any point in space.
But it's still possible that you wouldn't find it there.
It is very possible we're going to look somewhere and not find it because it has a certain probability, right? It's like when you're playing a card game. There's only a certain probability of getting a certain hand. It can happen, but there's also many other probabilities. Matthew?
The previous, or from N1 to N2, there's a trough, where there's a trough in number 2 where there's a peak in number 1, and then there's a trough in number 3 where 1 and 2 peak.
Are you referring to the things I circled? All right, now here's something that's going to blow your mind a little bit more. It's all about probability, okay? So there is a probability in 2s to find the electron on the inner side, kind of the point that Jackson was getting at. There is a probability of finding the electron close to the nucleus in n equals 2. There is also a much larger probability of finding it further away from the nucleus. What do you think the probability is between those two places? What does that mean? You can either be here or here, but you can't be in the middle. There is 0 probability of finding in the middle. Why does that hurt your head? How does it get there? Like, we think about things traveling in a path, and there's no path because then the path it would cross would be going through one of these places called a node.
Yeah, but it'd have to, but if it didn't do that, it would break pretty much everything that we know.
It would. So, if you can wrap your head around it, it can be here or here, never in between, and the probability of finding it is non-zero on both sides, but 0 in the middle.
So on the 2S that we're discussing right now, that candy shell, it's like completely open, right? There's no 2 shells in there, right? It's just 1.
Well, so for n equals 2, there's actually a probability of finding the middle. There's a node, the white, and then there's a probability of finding it outside. Is that what you're referring to? So the candy shell just represents within that sphere, there's 90% of the probability is contained, but there are nodes within that 90%. So it's not equal distribution within.
Okay.
All right, so let's, quick question?
Okay, so whenever I was reading, it said that
Nice and loud so everyone can hear.
the L value equals 0.
You're talking about the quantum numbers? Okay, so let's discuss that after class. So the second type of orbital we talked about are p orbitals. P orbitals exist with the probability density on either side of the nucleus. Take a guess at what the probability distribution is at the nucleus. 0. What do we call that when there's a 0 probability? Node. That's a node. So once again, one electron can occupy this orbital. There's a 50% probability of being above the axis, 50% of being below, 0 of being in the middle. One electron. It's not like we have one electron on each side. It's one electron, 50% probable of being on either side with 0 in the middle. And so there are 3 different types of P for every shell. There's PX, PY, and PZ. And they're perpendicular to each other. So there's 3 axes, right? The X, the Y, and the Z axes. So they're the 3 different axes. Once again, the candy shell represents where about 90% of the probability is. Very quick comment?
Yes.
We only have a couple minutes left.
What about the fact that if there are 3 of those and they start in the shell n equals 2, if you look at the group, there are 6 in that group.
6 electrons, but there can be just 1 electron, and it will still have a 50% probability on either side. We can't have 2 electrons. Then there's a probability of having both here, 1 on each side, but never to have them in the middle. So we can look at the distribution functions as well. If we look at all of them overlapped on top of each other, this is kind of what the 3 different p orbitals look like when they're overlapped on top of each other. This will become very important when we start talking about shapes of molecules. The p orbitals are where some of that shape comes from for double bonds and those kinds of things. There's also d orbitals, and d orbitals have 5 different shapes that they can look like, and these are the probability distributions of the 5 different d orbitals. And when they overlap each other, it just looks like a whole bunch of mess of these orbitals. And so I don't think we have a diagram with all of those overlapped on top of each other. So let's go back to Bohr's model of the atom. Bohr's model of the atom was n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. It's going on and on. That was true when he was looking at one element and one element only, and that was hydrogen. As soon as he looked at any other element, this model fell apart. And so he just kept studying hydrogen for the most part until some other people came and helped him out. And so what it turns out is when you look at hydrogen, neutral hydrogen, there's only 1 electron. So that electron can move between n equals 1 and n equals 2, and there's no interaction with any other electron because there's just 1 electron. That's it. So this is basically what Bohr was looking at. He was looking at a highly oversimplified n equals 2. n equals 2 has actually 2s and 2p in it. n equals 3, he didn't realize it, had 3s, 3p, and 3d. All those different places that electron could go, but they're all equal in energy because there's no repulsion of any other electrons. Once you start adding more electrons, now that s orbital is actually more stable than the p orbital. And so you start to see that the 2, n equals 2, has 2s and 2p, and that those are differentiated levels and higher energy requirements to go into n equals 2p than into 2s. And so what I want us keeping in mind is that the vertical axis here is the amount of energy, or the relative level of energy for each of the different electron levels. And so we're going to start filling in these atomic orbitals. So this is an atomic orbital diagram. And before we leave class, I'm going to have you answer this question. We're going to be using this exact layout of orbital diagrams, atomic orbital diagrams, and you're going to be using this to identify elements, and you're going to be filling in these 4 elements. So talk to your neighbor, try to figure out what element this is representing, if it's a neutral element. Okay, so can I hear from a volunteer? Kayla? Okay, why do you say that? How many electrons? So 1, 2, 3, 4, 5, 6. Each arrow represents an electron with half of a barb. So if it has 6 electrons and it's neutral, how many protons does it have? Which is carbon. Close. They just missed counting. All right, so next class, I'm going to have you guys filling these out. I believe that your pre-class assignment had some of this. And I'm going to write up the configuration here so you guys can see it as you're leaving if you're interested. Please come to office hours, talk with me about this kind of stuff. where I love helping you figure out why these things work the way they do and the connections between them. Yeah, so F starts way after, and there's some differences in energy.
I understand this, but like, is there any calculations that they're
There are some, but we're not doing it at all.
we're not, so they're not always done it? Okay, but I get that.
There's a math question.
Okay.
And screwing me up on homework last week really bad.
Okay. Can we talk about it as I deconstruct my